at least people using modern operating systems would have been protected from some of these exploits. Another popular exploitation technique is overwriting overwriting exception handler function pointers on the stack. So, for example, if you've got a stack buffer overflow, instead of overwriting the return address, you could overwrite a function pointer that got pushed onto the stack when you entered into a block protected by an exception handler. And there are a couple of mitigations that Windows has that can help you with this. And the first one, which has been around for a long time, is called SafeSEH. And SafeSEH basically uses the toolchain to insert a table of known good exception handlers within every module. So when Windows gets an exception and picks up the pointer to the exception handler from the stack, it can verify that against the table to see that it's actually a known good exception handler before it jumps to it. And this is controlled by or you can actually use the SafeSEH linker option to make sure that your modules do have this table of known exception handlers within the module. This has been around forever as well, but not everybody makes sure that they actually do have it in place. And if you as an application developer don't have this in place within all modules of your application, then the user won't benefit from the exploit mitigations in Windows. In Vista Service Pack 1 and later operating systems, there's an even better exploit mitigation for SEH overwrites, which is called SEHOP, or SEH overwrite protection, which actually checks the integrity of the whole chain of exception handlers all the way back down to the default exception handler, which is much stronger, and to date there hasn't been any practical ways to circumvent this protection. Unfortunately, in Vista and client systems, this isn't enabled by default. So as an application developer, it's hard to make use of this because it actually has to be enabled on each client platform. On servers, this is enabled. So if you're writing server applications, then you probably will benefit from that protection. But a lot of client systems today aren't hardened to the level that they've enabled these features. Two other features that you probably heard of already, but worth mentioning because you need to be aware of them as an application developer, are DEP and ASLR. Now, data execution prevention is basically making use of the page permissions that we talked about earlier to make sure that, for example, the pages containing the stack cannot be executed. So you can no longer insert shellcode in your buffer overflow in the buffer that overflows the buffer on the stack. So it basically sets the executable bit only on memory pages that contain executable code. Unfortunately, for backwards compatibility reasons, this isn't enabled on all systems. So client systems still doesn't have this enabled for every process. So I won't go through which systems have which policy, but there are different policies like opt-in, opt-out, always on, always off. Always on, always off are self-explanatory. Opt-in means that a process needs to be DEP aware and say, I support this, please enable DEP for my process. Opt-out means that it's used for all processes except for certain processes that are on an exclusion list. There is a way for you as an application developer to actually enable this for your process on all systems except the always-off systems, of course. which is by calling set process depth policy API. And that's basically a one-time call that you can do in your initialization routines that will enable depth for the whole process and will make it impossible to turn off depth for that process as well. So you can't call it again to turn it off, for example, as a step in an attack. You also need to be aware of the nxcompat linker option, which you should be using to make sure that the modules that you produce indicate that they are depth compatible. The other feature, ASLR, which is new to Vista and later operating systems, complements depth by making it harder to work around or circumvent depth. One of the easiest ways of circumventing depth from the start was using something called a return to libc style attack. Basically, overwriting for example, a return address, forging a stack frame before it that would be interpreted as parameters to the function that you are diverting execution to. So then you could divert into, for example, the virtual protect function, and using that, turn on the execution bit for the memory pages where your shellcode lived before you jump to them. And to make that harder, ASLR randomizes the memory addresses where all executable modules are loaded on different systems. So I think there's about a byte of entropy in there. So there are about 256 different places where your module could end up in memory, which makes it much, much harder to make a reliable exploit that circumvents depth. Like I said, available in Vista, and you need to be linking all your modules with the dynamic base linker switch to make sure that you can use ASLR on Vista. Right. I hope that was somewhat clear. If it's not, please go read the white paper. Like I said, I spent at least reasonable amount of time making sure that the information in the white paper is correct and that it's easier to read and understand than what I'm presenting here today. This is actually the heart of the talk. This is what got me started in making this presentation. A lot of the big vendors today, like obviously Microsoft, but a lot of the big third-party vendors like Adobe, have been targeted with a lot of attacks and are feeling the need to step up their game a bit, and are starting to use these features that Microsoft themselves have implemented into Windows and into the toolchain to secure Windows and Microsoft applications, and making use of those to secure their own applications. So, for example, the kind of sandboxing I was talking about earlier, where you use, for example, a restricted token to spawn off a new process with low privileges, is something that Microsoft have used in Office 2010. And Adobe, in their new Adobe Reader 10.0, will actually implement these features, sandboxing features, and will sandbox off their PDF parser so that it will run with low privileges and hopefully mitigate a lot of the PDF exploits that we're seeing today. So, what can we learn, basically, from Microsoft's almost 10 years journey into trusted computing? Well, we can start to use these exploit mitigations that are available to us both in the toolchain and in Windows, which means that we need to be aware of them and how they work and how we need to, in some cases, enable them for our apps. And always build with the latest toolchain. If we're not using the latest version of Visual Studio, for example, the /GS stack overwrite protection will be significantly weaker than it would be if we're using the latest version. So always make sure that even old modules that you might not have changed actually get rebuilt with the latest version of the toolchain for each release. We can also read the Microsoft SDL and adopt certain practices from it that make sense in our development environments. One thing that I'm particularly fond of is actually doing architecture review and looking at your application not as an application as a whole, but as interconnected modules that each have an interface to the rest of the application, basically breaking it down into manageable chunks that we can look at and say, what are the inputs to this and how do I secure it? There are also interesting guidelines for secure coding in the SDL. For example, there's a list of banned APIs such as strcpy and memcopy APIs and stuff like that. And of course, secure or more safe, I should say, more safe counterparts that you should use instead. So try to learn from Microsoft in that respect. They've also developed some interesting libraries and C++ templates over the years that you can also use in your applications. So for example, there's a C++ template library called safeint that can be used to basically get rid of integer arithmetic errors. So for example, integer overflows where you've got two values that you add together and the value is too large to fit into an integer and it wraps around, leading to, for example, incorrect calculations for allocations of buffers or copying of memory and stuff like that. There's also a C variant of that called intsafe.h, which is in the Windows SDK. And as I said, the list of banned APIs is interesting. It's integrated into Visual Studio, so Visual Studio will now tell you that this is deprecated, you shouldn't be using this. And there's actually, if you're lucky enough to be able to compile your code using the C++ compiler, there's something called secure template overload, which can actually take your strcpy, memcopy calls and directly translate that source code when compiling into the safer counterparts. So you don't actually have to go in and fix all your code. It can do that automatically for you. Something to check out as well. Something that I wasn't aware about until quite recently, pointed out to me by a friend who said, "Oh, you're talking about exploit mitigations. You should check out Emmet." And I said, "What's Emmet?" And I was actually fortunate enough to speak to one of the developers of Emmet earlier on today, and it's pretty cool. Admittedly, it's something that might not be very useful to third-party developers, but you should at least check it out. It's very interesting. Emmet has taken some of these mitigation techniques that we've talked about that are available on Vista and above and ported them, for example, SE hop, that's only available on later operating systems, and ported it into something that's compatible on XP as well. And also there are some features in Emmet that can enable, for example, ASLR and DEP for your processes without you actually having to do all this, be aware of all this stuff that I've been talking about before. So it can, for example, force modules to